Good morning students, welcome to Bindu Dhadwal chemistry lessons. We are doing the chapter hydrocarbons. Our topic for today is preparation of alkenes and physical and chemical properties of alkenes. The first method of preparation of alkene is from alkynes. So alkynes on partial reduction with hydrogen with palletized charcoal, which is partially poisoned with compounds like sulfur compounds or quinoline, will form alkenes. One of the pi bond will break and one hydrogen will be added on this carbon and one on this carbon. As a result, our CH double bond CHR is formed, and the alkene formed is cis alkene. Whereas on reduction with sodium in liquid ammonia, we get trans alkene. Hydrogen is added on opposite sides of the double bond. This catalyst, palletized charcoal poisoned with sulfur compounds or quinoline, is called Lindlar's catalyst. It is called Lindlar's catalyst. Next method is from alkyl halides. When alkyl halides are heated with alcoholic potash, that is potassium hydroxide dissolved in alcohol, say ethanol, alkenes will be formed. What happens is that the halogen and hydrogen of beta carbon will combine to form HX, which combines with QH to form KCl and water. So as this is eliminated, a double bond is formed and alkene is made. So this reaction, because one hydrogen and one halogen is being removed, it is called dehydrohalogenation reaction. D means minus and hydrogen and halogen are being removed. It is also called beta elimination because along with the halogen, the hydrogen of beta carbon is removed. The nature of halogen atom and the alkyl group will determine the rate of the reaction. For example, iodine will be the most reactive, then bromine, then chlorine, and amongst alkyl halides, the tertiary alkyl halide will be most reactive, then secondary, then primary. Next method is from vicinal dihalides. Dihalides in which the halogen atoms are attached to adjacent carbon atoms are called vicinal dihalides. When these vicinal dihalides are treated with zinc metal, zinc will combine with the two halogen atoms to form, for example, in this case, bromine atoms to form zinc bromine, and a double bond will be formed and alkene will be formed. From alcohols by acidic dehydration. So when alcohols are heated with concentrated sulfuric acid, again elimination occurs. H and OH will combine to form water and a double bond will be formed here. So as this elimination occurs in the presence of acid and water is removed, so this reaction is called acidic dehydration. Dehydration means removal of water. This is also an example of beta elimination. The carbon to which the functional group is attached is alpha and the carbon next to it is beta. So the OH and hydrogen of beta carbon are being removed. So it is also an example of beta elimination reaction. Properties. Physical properties. The first 3 members of alkenes are gases. Next 14 are liquids. Higher to them are solids. Ethene, the first member, is colorless and has a faint sweet smell. Other alkenes are colorless and odorless, insoluble in water but soluble in organic solvents, non-polar solvents like benzene, carbon tetrachloride, etc. Alkenes show a regular increase in boiling point with increase in size. Every CH2 group added will increase the boiling point by 20 to 30 Kelvin. With the increase in size, the van der Waals forces of attraction increase, become stronger, so the boiling point increases. Straight chain alkanes will have higher boiling points than isomeric branched compounds. This is because straight chain have more surface area, are bigger molecules, whereas with branching, the molecule acquires a spherical shape, has lesser surface area, and so lesser van der Waals forces of attraction. Chemical properties of alkenes. Alkenes are rich source of loosely held pi electrons, due to which they show addition reactions in which the electrophiles, that is positively charged species, add on to the double bond to form the addition products. Some reagents, addition reactions occurs which are electrophilic in nature, but some addition reactions may also occur by free radical mechanism, and in special conditions they may also undergo free radical substitution reactions. So let us do the first chemical property, addition of dihydrogen. So when dihydrogen is added to alkene in the presence of catalyst, say platinum or palladium or nickel, a bond breaks, a hydrogen is attached here and another here to form a single bonded compound, alkane. Ethene will form ethane, propene will form propane, and so on. Addition of halogens. Halogens like bromine or chlorine add up to alkene to form vicinal dihalides. This occurs in the presence of carbon tetrachloride. A bond will break, one Br will get attached here and other will get attached here to form 1,2-dibromoethane. 1,2-dibromoethane or vicinal dihalide. Because the reddish brown color of bromine is discharged, so this reaction is also used as a test for unsaturation. If on adding bromine to a compound, a bromine dissolved in CCl4 to a compound, if the color gets discharged, it becomes colorless from reddish brown color, then that means alkene is present or unsaturated compound is present. Similarly, propene when reacts with chlorine will form 1,2-dichloropropane. Addition of halogens is an example of electrophilic addition reactions. A chloronium ion will be added first and then the chloride ion, and a cyclic intermediate is formed. So the reaction involves cyclic halonium, that is positively charged halogen ion formation. Addition of hydrogen halides. Hydrogen halides will be added to alkenes to form alkyl halides. The order of reactivity is hydrogen iodide is more reactive than HBr is more reactive than HCl. This is because as the halogen atom increases in size, it's easier to break the bond. Addition of hydrogen halide is also an example of electrophilic addition reaction, that is first positively charged hydrogen will be added and then negatively charged bromine will be added. So addition reactions can be categorized into two categories. Addition of HBr to symmetrical alkene, one atom will have H and one will have Br to form the only one product, ethyl bromide, if it's added to ethene. Similarly, but2ene, when HBr is added, only one product, 2-bromobutane will be formed. But when addition of HBr is added to unsymmetrical alkenes, then the addition occurs by Markovnikov's rule. Markovnikov's rule states that the negative part of the adding molecule will go to that carbon atom which has lesser number of hydrogen atoms. So this is an unsymmetrical alkene. One carbon has one hydrogen, another has two hydrogens. So negative part will preferably get attached to that carbon which has less number of hydrogens, so that although both the products are formed, but this will be formed in greater proportions. It's the major product. And on the other hand, the 1-bromopropane will be formed in lesser amounts. So according to Markovnikov's rule, the rule states that the negative part of the addendum or adding molecule gets attached to that carbon atom which possesses lesser number of hydrogen atoms. We can understand why this happens by the mechanism of the reaction. Hydrogen bromide will provide an electrophile H positive which will attack the double bond to form carbocation. So these when HBr releases H positive will take these electrons and will form carbocation, get attached and form carbocation. Now two possibilities arise. Either H gets attached here and positive charge comes here, the electrons of double bond move here, and because they move here, H will also get attached here. From CH it gets converted to CH2, and because electrons have moved from here, this carbon gets positive charge. So either this is the possibility. In this case, a primary carbocation is formed. The positive charge resides on a carbon which is attached to only one other carbon atom. But in the other case, the possibility is that the electrons move here and H also gets attached here. Then positive charge comes on the central carbon atom, and this kind of carbocation that is formed is secondary carbocation. So two possibilities are there. A primary carbocation may be formed or a secondary carbocation may be formed. But because secondary carbocation is more stable, the possibility of this being formed is greater. Even if a primary carbocation is formed, in order to stabilize itself, it gets converted to secondary carbocation. So this is the major product, major intermediate. Then in the next step, the secondary carbocation will take up the Br atom to form 2-bromo-alkane, or the primary carbocation, if it is formed, will take up Br to form primary bromo-alkane. So because this is secondary carbocation is formed in major amounts, the secondary product is also in more proportion than primary. Anti-Markovnikov's. This was Markovnikov's addition, where negative part of addendum goes to the carbon atom which contains lesser number of hydrogen atoms. But if the same reaction is carried out in presence of a peroxide, then addition occurs contrary to Markovnikov's addition. Such kind of addition is called anti-Markovnikov's addition. The effect of peroxide is called peroxide effect or Kharash effect also, because it was discovered by Kharash in 1933. M.S. Kharash and F.R. Mayo observed this effect in 1933 in honor of the scientist. This is known as Kharash effect. See, the reaction is that unsymmetrical alkene and HBr will react in the presence of peroxide. In this case, this is benzoyl peroxide, and Br will get attached to this carbon and H will get attached here. The product will be CH3, CH2, CH2, Br. 1-bromopropane is formed. So mechanism, peroxide effect proceeds via free radical chain mechanism. First, the benzoyl peroxide will break homolytically. Homolysis means the bond will break into two equal parts. One electron goes here and another goes here to form this C6H5COO with one electron. Now this is unstable, so carbon dioxide gets eliminated and bond breaks again to form phenyl free radical. Now in the next step, phenyl free radical will react with HBr and will break this bond also homolytically, take the H to form C6H6, and Br free radical is generated. This Br free radical can again react with an alkene and cause the homolysis of the pi bond. So the electron may either come here or may come here when this bond is broken. One of the H is taken to form HBr. So one H with electron is taken with and combines with Br with electron to form HBr, and one electron of the pi bond is left here. If it's left on this position, it will form a primary free radical. If it is left on this position, it will form a secondary free radical. The carbon here is attached to two other carbons, so it is secondary. Now, secondary free radical is more stable, so this will be formed in greater amounts. And in the next step, this secondary free radical will combine with another HBr molecule and take the H to form CH3, CH2, CH2Br, major product. And the Br with one electron, because this bond is again broken homolytically, Br with one electron, another free radical is generated. So this reaction keeps on repeating. Once Br is formed, it will react and again produce another Br free radical. Now, if a primary free radical is formed, then in that case, it will take H of the HBr to form minor product. So both major and minor products are also formed in peroxide effect, but the 1-bromopropane will be formed in greater proportions. So secondary free radical obtained is more stable than primary, so 1-bromopropane is the major product. Now, peroxide effect is not noticed in addition of HCl and HI. It is only noticed in HBr. So it's not noticed in HCl because HCl bond is stronger. The bond enthalpy is 430.5 kilojoules per mole than the HBr, whose bond enthalpy is 363.7 kilojoules per mole. So it is not cleaved, so this peroxide effect is not observed here. And HI bond is weaker than HBr bond. Its bond enthalpy being 296.8. But when it breaks, the iodine free radical will combine with themselves to form iodine molecule rather than getting added to the alkene. So this effect is also not seen in case of HI. Only in case of HBr we see Harash effect. Next is addition of sulfuric acid. Cold concentrated sulfuric acid will be added up to ethene in such a manner that H goes to one carbon atom and OSO2OH goes to other carbon atom to form ethyl hydrogen sulfate. But in case of unsymmetrical alkene, the negative part of the addendum or adding molecule will go to the carbon atom which contains less number of hydrogen atoms. It is Markovnikov's addition. So, propyl hydrogen sulfate, isopropyl hydrogen sulfate will be formed. Addition of water. In the presence of a few drops of concentrated sulfuric acid, alkenes will react with water. Water will get added up. Again, Markovnikov's addition occurs and OH will come to carbon containing less hydrogen atoms and H to carbon containing more hydrogen atoms. OH2 methyl propane 2O is formed. Oxidation. Alkenes on reaction with cold dilute aqueous solution of potassium permanganate, this is called Bayer's reagent, will produce vicinal glycols. The water and O will form two OH which get attached to both the carbons. One bond breaks and OH gets attached here and OH gets attached here to form vicinal glycol, that is two hydroxy groups on adjacent carbon atoms. This is ethane 1,2 diol, also known as glycol. If this is added to unsymmetrical alkene, then also one OH here and one OH here, we get propane 1,2 diol. This was aqueous solution of potassium permanganate. If acidic potassium permanganate or acidic potassium dichromate is used as oxidizing agent, then it will oxidize it into either ketones or acids or both, depending upon the position of the double bond. The reaction occurs in such a way that the double bond breaks. One oxygen will be added here to form CH3, CH3 double bond O. This is a ketone. And one will be added here HCHO will be formed, CH2O, but it will further get oxidized into carbon dioxide and water. So if the double bond occurs at the terminal position, one of the products is always carbon dioxide and water. And in case it's not terminal, the double bond is present in between the molecule, then it will break from here. One oxygen gets added here to form aldehyde, another gets added here to form aldehyde, and two aldehydes will be formed, but they will be further oxidized into ethanoic acids. So with the acidified potassium permanganate, the oxidation occurs in such an extent that either ketones and or acids will be formed depending upon the nature of alkene and the experimental conditions. Next reaction is ozonolysis. Using ozone, we can also carry out oxidation. So ozonolysis means ozone is added and it will break down during addition. Lysis means breakdown. So ozonolysis of alkenes involves the addition of ozone molecule to alkene to form ozonide, and then the cleavage of ozonide by zinc water to smaller molecules. This reaction is highly useful in detecting the position of the double bond, where the double bond is located in the alkene. For example, when we add ozone to propene, both these double bonds will break. So we get CH3, CH and CH2. Both the bonds are broken and the O3 molecule will get attached on these two carbons where there was a double bond. So to form this structure, one oxygen above CH2 and two oxygens below, and a cyclic intermediate is formed. This product is called propene ozonide. Propene, the original reactant, and because ozone has added to it, ozonide, propene ozonide is formed. When this ozonide is heated with zinc and water, homolysis occurs of these two bonds. Similarly, these two bonds. So one of the product is CH3, CH. When the bond breaks into two parts, one electron from here and one electron from here will form a double bond here. So the product will be CH3, CH double bond O, that is CH3, CHO. And this product will be HCH double bond O. So this is formaldehyde. And this oxygen will be taken away by zinc. So because by adding ozone, we get the products with respect to the position of double bond. Wherever there is a double bond, you add an oxygen to either side. So one of the product is CH3CHO, other product is HCHO. So because the products will give the indication where the double bond is located, you simply have to join CH3CH with CH2 to get the position of double bond. So this reaction is also used to determine the position of the double bond. Similarly, when 2-methylpropene is reacted with ozone, ozone gets added here, the double bond will break and this hut-like structure will be formed. Then with zinc and water, homolysis will occur. So CH3C double bond O, CH3 will be formed, which is propanone or acetone, and HCHO will be formed. So accordingly, we can find the products. Then next reaction is polymerization. Polythene is obtained by combination of large number of ethene molecules at high temperature, high pressure and presence of catalyst. So the product formed is called polymer and the process is called polymerization. Similarly, propene will be added to form a product with high molecular mass, where propene is added again and again to form the polymer. So polymerization of propene will lead to polypropene, polymerization of ethene will lead to polyethene. So what happens is that at high temperature and pressure and in presence of catalyst, one of the bond breaks and two valencies are freed. So on either side an ethene molecule can be added. For every ethene there is a breakage of bond and one ethene will get attached to another, which will get attached to another to form a long chain called polymer called polyethylene. Similarly, polypropylene. These polymers are used for manufacture of plastic bags, squeeze bottles, refrigerator dishes, toys, pipes, radio and TV cabinets, etc. Polypropylene is used for the manufacture of milk crates, plastic buckets and other molded device. So that's all about alkenes. If you like the video, please do share and subscribe. Thank you. Have a nice day.